Okay, so about me, there's a standard introductory blurb, but the thing which really excites me, the thing which really floats my boat is essentially kicking the back out of the database engine. I like to play around a database engine at home. I come up with various workloads to put it under extreme stress, and what I like to do is I like to see where the outer edges of the database engine are in terms of performance. Okay, and in doing that, I usually dive deep into the internals, so people that have seen my stuff before, seen me present, will be familiar with the fact that I like to use Windows Performance Toolkit a lot, so I like to see everything that the database engine is doing under the covers. The other thing I like to do is I like to use the fastest storage I can get my hands on, because I have a tendency to set up my test environment such that I'm not waiting on I/O, such that it's predominantly service time, i.e. what's happening on the CPU. Okay. The OLTP application, radically different to an OLAP application. None of this should come as a surprise to anybody, but I'm just going to ramp up gently before I go into the more sort of deep stuff. So if you've got an OLTP application, what does it look like? Well, typically we're talking about short transactions. We're talking about T-SQL statements and transactions which only affect a handful of rows. Unlike an OLAP application where you can have end users concocting weird and wonderful T-SQL and firing off statements against a database at their heart's whim. You'll have like a fixed set of T-SQL statements. The I/O invariably tends to be random in nature, and the final point is that OLTP applications tend to be very log write sensitive. Okay, so I appreciate that people that are watching this material might not have a pure play OLTP application, so not everybody out there will be working on something like an airline ticket booking system or some e-business or software as a service type offering. However, I'm hoping that there's still something for everybody in this session. Okay, so very quick OLTP checklist. As I mentioned, log write latency is critical to a point, and I'll get on to the actual reason why I said it's critical to a point further on in this session. OLTP and OLAP don't play nicely together historically. So one of the aims, usually with an OLTP application, is to fit your sweet spot of data in memory to have a nice page life expectancy. If you have OLAP type users and they're coming along, they're in your opinion polluting the plan cache, issuing statements which are performing big partition scans, scanning large objects, that's not going to work very well for the performance, scalability, and the having a OLTP workload with predictable response times. Okay. Typically, you want fine-grained locking, and preferably no lock escalation. There's a couple of trace flags for controlling that you might consider using. Another point is to avoid compression for OLTP. Again, you don't want the overhead of having to compress pages. that can work well for OLAP applications whereby you've got much superior CPU capacity to storage I/O bandwidth. It's not so great for OLTP, and certain plan shapes suit OLTP applications best. Okay, I do apologise, I've got next slide there. I haven't got a slide on that, so I'll tell you what sort of plan shapes I'm talking about now. So typically, with a query plan for an OLTP query, you want nested loop joins, you want ideally single-threaded queries. There are a couple of people in the community who say that you should go for a degree of parallelism of 2, for the simple reason that that gives you Bloom filters in your execution plan. You want to avoid blocking iterators where possible, things like sorts, things like spools. There's a notable exception being the index. There's an index performance spool. Also, I'm sure Craig Freeman's got it on his blog somewhere. There's also like it's almost like a hidden spool, so that the database engine can sort of pre-order data before you're performing index key lookups. But by and large, spool operators and spool iterators and blocking iterators are not good news for OLTP queries. Okay, so your OLTP tuning toolbox. Okay, so let me just run through these. There tends to be two sets of tools. There's tools which are associated with simulating a workload or capturing a workload. So there's this thing called RML utilities, which is free from Microsoft. There's another free tool called HammerDB for simulating TPC-C and TPC-H workloads. I'll give you a demo of that. There's also this thing called the distributed replay, which actually comes with SQL Server. So there's a bit of overlap between RML utilities and the distributed replay agent. The key thing is that the distributed replay agent is actually packaged as part of the database engine install. Okay, so we have diagnostic tools and tools for capturing performance stats. So there's this free tool on Coplex called PAL, or Performance Analysis of Logs. To give it its full name, you collect a perfmon collector. You create a perfmon collection file, and you load it into this tool, and it's got a number of predefined thresholds, and it'll give you a bunch of nice graphs. And it uses a red, green and amber traffic light system to tell you if you've got things which are bad, things which are okay, and things which are good. So that's a tool I've used and that I recommend. Extended events is another tool, perhaps not necessarily something you'd have on all the time on production systems, but I do know of people that do this. It's something I'm only going to touch on. It's a subject that Jonathan Cahias from SQL Skills has blogged on at length. Dynamic management views. Every DBA's friend. So there should be some usual suspects there which immediately spring to mind. So sysdm OS wait stats, virtual file IO stats. If anybody's after some free scripts which run against the dynamic management views, I recommend Glenn Allenberry's diagnostic scripts highly. My old favourite, Windows Performance Toolkit. It's a deep dive tool. I'll show you that later on. It's probably not something that many people would use. It's really a seriously low-level diagnostic tool. Okay. SQL Diag, again, it's I believe that's it does come with the database engine. It's under the SQL Server install. That can be used for capturing a whole bunch of stats. It's usually if you deal with Microsoft support, they will either get somebody to run this or ask you to run it for them. And finally, SQL Profile. Okay. So in terms of those tools, the things that you'll probably use on a day-to-day basis to monitor a production system in Angular will be perf1 counters, which I should have put on there, dynamic management views. Again, people might write their own scripts to actually dump those out into a table. Extended events, things such as Windows Performance Toolkit and PAL, and also SQL Diag. They're more sort of when you've got an issue which requires you to perform some sort of active investigation. Okay, so tools can be great, but there's one big problem, and that is that you need to know what you're looking at. I've seen people that have got their hands on various tools and they get incredibly excited about having a particular tool, but how can I put this in the nicest way possible? They don't necessarily fully understand what they're looking at. Okay, this slide is a bit tongue-in-cheek. If I was given the choice, I would prefer a crude tool and a good understanding of what sort of stats the tool is pulling back, rather than an all singing and dancing tool and little or no understanding of the stats that the tool is pulling back. Okay, so the takeaway here is that actually having some concept of the stats that you're looking at rules over having a shiny or singing or dancing tool. Okay, so what gives us the biggest bang for our buck? Typically the schema design is the sort of foundation where performance is laid down. It's ironically, it's not something that people talk about that often, but it's just so important, and it's so intrinsic in the performance and scalability of an application. You get that wrong, and anything else you do, you're just really sort of using sticking plasters. Okay, indexing strategy should come as no surprise. And then finally your T-SQL code and the way you design your code. Okay, so that sort of accounts for the sort of rump of the stuff which will give you most of your bang for your buck. Okay, so once you've got all that stuff sorted out, what you're typically going to run into are things around synchronization primitives. So we're talking about locks, latches, and Spinlocks. And then finally, it's something I've talked about and I've presented on is that if you're pushing the database engine particularly hard and you're pushing it in specific ways, there's aspects of the CPU architecture which you'll see through the behaviour of the database engine. So I'll give some examples. Large memory pages. The way that works is you've got part of the CPU associated with the memory management unit which contains essentially map on how physical how virtual memory is mapped to physical memory. Okay, that is an aspect of how the physical CPU sort of sticks its head up and how it can sort of affect our performance. So you use large pages. If you can actually look up the virtual to physical memory mappings on the CPU, as opposed to having to go out to main memory to look at the memory map in main memory, that will give you some performance benefit. Okay. Also, on something I'll get onto, Spinlocks, it plays a massive major role in Spinlock behavior, and that's something that I will cover later on. Okay. So I mentioned that you need to know what you're looking at of a tool, so what I'm going to start off with some of the basics. Okay. So in terms of synchronization primitives, and we're talking about the default database engine here, there's three usual suspects. There's locks, latches, and spinlocks. A lock is something that's associated with the transactional behavior of the database engine, and it's used to enforce isolation levels, and it's something that can most definitely be controlled in the application via hints, indexing, how you touch the rows, the order you touch them in, whether there's an index there or not. How you code your T-SQL can have a massive impact on how often, how long locks are held for. A latch is a subtly different beast. It's used to protect internal memory structures inside SQL Server. It's not something that you can directly influence per se. Off the top of my head, there might be a trace flag for influencing the behavior of super or sub latches, but that is your lot. You're extremely limited in the way that you can directly control latches. As I said, there's perhaps only one knob that I know of which allows you to influence latch behavior. But the one takeaway about locks and latches is that if you can't, if you need to acquire a lock in an incompatible mode with a lock that's already been taken out on the resource that you require, or you need a latch in exclusive mode, your session will go on to the waiting queue. Hence, you've got the Zs, which are intended to represent your sessions sleeping. There's one big problem with that, and that is if you've got a short uncontended wait for a resource, there's an overhead in yielding the SQL OS scheduler, and that's roughly around 200 CPU cycles. So for short uncontended waits, you're actually better off spinning on the result on this thing called a spinlock, and what that is a busy wait. So in layman's terms, what you're doing is you're going round in a loop, burning up CPU. However, there's a slight problem, and that is there becomes a point when this can become an overhead in itself, and this is something that I will cover further on into the material. Okay, so there's three types of latches. There's a page latch, which is associated with pages in the buffer pool. There's a page IO latch. So you'll typically see page IO latch _EX, which is a latch taken out when a page is read from storage for the purposes of being modified. There's page IO latch _SH, which is a page IO latch taken out when a page is being read for read-only purposes. There's a page IO latch _UP, which is a page latch associated with space management bitmaps, and then finally there's like a catch-all latch for all the rest of the latches, latch underscore. Okay, so common latching problems. There's one that springs to mind with most OLTP applications, and this is this thing called the last page problem. So we've got a logical representation of a B tree here. If you've got an index and it's increasing monotonically, i.e. the key is based on some value, usually numeric, which increases in order, and you've got multiple sessions trying to insert into the index, you'll get exclusive page latches on the last page in the B tree, hence the term last page problem. Okay, so one of the ways to get around this is to use a non-sequential key, and there's various things you can do. You can use a GUID, and that happens to be the most scalable index type here. You can craft a reverse key whereby you actually reverse the bits which represent the key value. You can hash partition your object. So what that means is that means you have a partition key, and before you actually insert the row, or when you insert the row, you use some sort of hashing scheme or hashing algorithm to actually hash the key value so that your inserts fall evenly across the partitions. And then there's another approach which is more for sort of test academic purposes. What you can do is you can use the sessions SPID as the starting point where you're going to insert into and add a massive value into it. And what that does is that keeps it prevents page splits, and it's after you've inserted so many rows, it stops each session from inserting into the same place in the B tree. Okay. So besides using a random key, something else that we can do is we can actually pad rows out. This works well if we've got a small number of rows. You absolutely won't want to use this if you've got some big transactional table. Okay. Another thing is this is the hash partitioning that I mentioned. So you can round robin between the B trees. So you hash partition a clustered index or a table of indexes, and basically you're distributing your inserts, your updates, your deletes across multiple B trees. Okay. So there's one obvious way of doing this which might spring to mind, and that is to use a sequence object. However, there's one big problem with this, because ta-da, a sequence object is actually protected by a latch. So you might elect to use this approach to go away from being killed by page latches, only to be hit by the latch which is protecting your sequence. Okay. So Spinlocks, how do they work? Okay, so there's some pseudocode here to illustrate how a Spinlock works. Okay, so a task will spin until it can acquire the Spinlock it's after. And the whole idea behind this is that for short uncontended spins, it's more efficient to burn some CPU than to yield a scheduler. Okay. However, we don't want to spin forever, so we've always had the concept of back off, and what that means is after so many spins we actually do give up the ghost, we yield the scheduler. SQL Server 2008 R2 introduced the concept of exponential backoff. So all that means is it means the longer we're waiting on the Spinlock, the amount of backoffs between actually yielding the scheduler and going to sleep decreases exponentially. Okay. So when is this a problem? Okay, so this is the one of the first techniques I'm going to dive into. Okay, so if you've got a transactional workload and your transactional throughput plateaus off, but your CPU consumption continues to rise, this is a red flag for having a potential Spinlock problem. This is great. This is in this technique appears in various Microsoft papers. Problem with this is that if you have a problem in a production system, you're not necessarily going to have a nice graph like this at hand. You're probably going to have something's going to flash up, and there's most probably going to be some requirement or demand somewhere for you to fix the problem yesterday. Okay, so this is nice, but it's not really, unless you've got a tool which produces this, it's unlikely to be something that you can readily create with the information you've got at hand. So what you can do is there's this really simple technique. What you can do is you can diagnose a Spinlock issue by doing the math. Maths for anybody in the UK, math for people in the US, and the main tool here is sys DMOS Spinlock stats. If you read up on this, you'll find you'll usually find that people make the comment, well, if you've got lots of spins, you might have a Spinlocking issue. So the $64 million question here is, what exactly is a lot of spins? So to quantify what's a lot, we need to take into account the elapsed time, our CPU clock speed, and also the number of physical CPU calls. Okay, so over a given window in time, we can work out how many CPU cycles have elapsed by doing some very simple maths. And then what we can also do is, if we know the number of spins that have taken place, what we can do is we can work out roughly as a percentage of the total CPU cycles how many spins we've had. So for this, all we need is we need access to sysdmos Spinlock stats. We need at least 2 data points, A and B, and we need to have some knowledge of how many CPU cores we've got, the clock speed, and also we need to know how long's elapsed between when those two snapshots of sysdmos Spinlock stats were taken. I'm guessing there'll be people who will either be watching this session or they'll watch the recording and they'll be thinking, well, that's great, Chris, but what about if I've got a virtual machine? Because I don't necessarily know how much of a bite of the cherry or physical CPU core I've got. So what I'd say to that is make your best endeavours to find out what your relationship between virtual processors and physical cores is, but also you can go on a very simple rule of thumb. So based on the fact that most modern processors have clock speeds of the order of gigahertz, so that's a gigahertz is a US billion CPU cycles per second. Very roughly, you need to have spins of the order of billions to have a Spinlock problem worth worrying about. Okay. So Something else that I want to touch on, another troubleshooting technique, is write log performance. So out there in the community, there's this notion that if you've got write log waits, you have slow storage. This, to a high degree, for much of the time, is correct. However, you can get into a situation whereby your average write log waits can be higher than your write stalls on your transaction log. Okay, and what this means is, that your write log waits are not necessarily down to poor performance. So what you have is, you have a number of Spinlocks protecting the login infrastructure, and again we're still on the disk row store engine. The main tool for looking at this is still SysDMOS Spinlock stats, but what you need to do is, if you notice that your average write log weights are higher than your average write stalls on your transaction log, you need to start looking at the key Spinlocks around the login infrastructure. Okay, and there are two main ones. There's a thing called log cache access, and there's another one called log flush queue, and I'll go over what they actually represent in a nice diagram. Okay, so at the top of our logging infrastructure, and again, we're talking about stuff which takes place before the login information has been hardened to the transaction log. We've got this thing called the log buffer. Okay, so at the top you'll see this log cache underscore access Spinlock that needs to be acquired before a session can copy its information into the log buffer. At the bottom, we've got this thing called a log flush queue Spinlock, which the log writer needs to take out before it can actually harden the login information to storage. Okay. Quick mention of SQL Server 2016. SQL Server 2016, if you are running your database engine on a machine with more than one CPU socket, and I mention this because people have said to me, oh Chris, I'm running SQL Server 2016 on a laptop and I'm not seeing this. You need to have 2 CPU sockets. What you get is, you get multiple log writers. It's usually 4 log writer threads on the first CPU socket or NUMA node 0. What can happen is, if you've got really low latency storage, and if you're using delayed durability, your log writer threads will be running that fast that they'll end up fighting each other, and you'll see lots of spins on log flush queue. If you see this, there's a trace flag 9038 which you can use to revert 2016 to the behavior of previous releases, whereby you only have 1 log writer thread. Okay, so if you see lots of spins and lots of backoffs on log cache access, your issue is at the top of the picture. If you see lots of spins and backoffs on log flush queue, it's at the bottom. However, a problem with the log writer not being able to do its job fast enough is that it can create back pressure on the log buffer. Okay, so if your average write log weights and your average write stalls are roughly the same or very, very close, your problem is more likely to actually be storage. Okay, but the point I'm trying to make here is that at scale, when I say at scale, based on the test I've done, you need at least 2 sockets, you need more than 6 cores per socket. You can get into a situation under very, very heavy workloads where it doesn't matter what your storage is, you'll end up hitting a performance brick wall around the log cache access Spinlock mainly, and also the log flush queue Spinlock. Another point to note is that in internal benchmarks that Microsoft have conducted, they're seeing cases whereby up to 40% of a server's CPU is expended on the log cache access Spinlock alone. Okay. So log cache access pressure. What can we do? There's a very, very rare circumstance under which you might want to play around the CPU affinity mask. So when your database engine starts up, this is another technique that you can use. Core 0 is assigned to the log writer, so we're assuming a single threaded log writer here. So what I've done is I've taken CPU 0 and CPU 1 out because I've got hyper-threading enabled. That means that the first two logical processes actually sit on CPU core 0. And what this does is this basically gives the log writer thread its own CPU core. And this can give us some performance in an increase in transactional throughput. Okay, so on this diagram here. Okay. So Spinlocks and memory. So everybody should know that the basic unit of transfer between storage and the sort of disk legacy engine is the 8K page. Okay. I want to go down a level. I want to go into memory, and I want to tell you about something, a low-level memory structure. If you go on something like the Intel developer forums, or if you go onto Stack Exchange and there's people on there that are writing performance critical code, they'll know about this object. I want you to know about it as well. This thing is called a cache line. It's a 64-byte wide memory object, and it's how memory is organized in the actual cache on the CPU. Okay, so you know about 8K pages on storage, you know about them in the buffer pool. I want you to know about cache lines in the CPU cache. So when we acquire a Spinlock, the cache line or cache entry has to travel from whatever socket and core the session has that's got that Spinlock, and it then needs to make the trip to the core and socket of the session that wants to acquire it. When that session releases it has to make the trip back. The key point of all this is that the further that memory cache line has to travel, the worse that will be for performance. So the best case scenario is that you've got two sessions running on the same CPU core. The sort of middling case is that both sessions are running on the same socket. The worst case scenario is that the sessions are running on different sockets. Okay, so and this is why this matters, because this has an impact, an influence on how well the disk space engine scales on hardware. Okay, so if we, using the CPU affinity mask again, if we execute a workload on NUMA node 0, which is where the log writer lives, which normally owns a log cache access Spinlock, using my test hardware, I managed to run a concurrent insert workload 18 threads on NUMA node 0, and it ran in 73 seconds. Okay, so if I run the same test again, but I change the affinity mask so that the only socket my schedulers can work on is socket 0, that takes much longer. And the reason for that is it's all about the distance that the memory cache line associated with the log cache access Spinlock has to travel. Okay, so you do it all on the same socket, and you will get you'll achieve certain efficiencies. It'll be better in terms of performance. Okay. And what we can do is we can actually quantify this in Windows Performance Toolkit. So this is another tool. I'll go over this later on. It's not a monitoring tool. There's companies that do have traces running continuously. However, they are not your normal SQL Server shops. These are organisations that are very sensitive to spikes in latency in transactional performance. So think things like online trading and sort of currency platforms, that sort of thing. Okay, so we can see here we've actually quantified the CPU time associated with that Spinlock, and we can see that by running the workload on the same socket as log writer, that we vastly reduced the CPU time associated with the spins and backoffs for the log cache access Spinlock. Okay, so tools for diagnosing Spinlock issues. So I've mentioned SysDMOS Spinlock stats, extended events, which I will give you a demo on, and finally Windows Performance Toolkit. Again, I will give you a demo on that also. Okay, so demonstration. So what I'm going to do is I'm going to spin up a simple OLTP workload. That's a TCPC benchmark using a free tool called HammerDB. And what I'm going to do is I'm going to dig into a particular Spinlock using extended events. So let me end the show. Let me minimize one or two things. So what I've got here is I'm going to look at this Spinlock, this thing called XDES Manager. Okay, so I need the map key and map value for that. So the map key is 113, which I'm going to. Hi Mark, are you?
Hi Chris. Yeah, I just wanted to say, could you just zoom in the into the text a bit so it's a bit bigger?
Yes. So voice in my ear is asking me to zoom into the text. So let's have a look. So
perfect.
Okay. So we're zooming into the text. So we're looking at this thing called XDES Manager. We get the map value of 113 for that. We down here in the results window. So I'm specifying that in the sort of where clause for the action part of the event. We're creating an event that's going to be fired off when we get a CQLOS Spinlock backoff event. Okay. So we need to specify a trace flag, and what that's going to do is that's going to make public debug symbol information available to the call stack that we're going to capture for this particular event. So we've got the call stack here, okay, and then what we're going to do is I've got here stop. We need to start that. In the best traditions of these programs where they make things with washing up bottles and sticky back plastic, I've run this already. I've already run this. I've run my dbcc command. All I need to do is I need to start my event session. However, there's one slight nuance I should point out, is that if you read upon this stuff, I believe that a lot of the material already out there, it mentions that you just need the what's called the public symbol file for SQL Serve. Okay, so if you read that, that is absolutely fine if you're running SQL Server 2008. If you're running on SQL Server 2012 onwards, you will need a few more public symbol files, and I'll show you what they are. Okay, so if I go here in this symbols directory, Let me just, so what we need is, let me look, SQL OS. So we need that one, SQL OS. We still need SQL Server DB, but we need more. SQL DK, SQL TSAS, SQL Min, SQL Lang PDB. Okay. There is also a public symbol file for Hackathon, the in-memory engine. You can play around that to your heart's content. You won't need that for Spinlocks for the simple fact that the in-memory engine is 100% lock-free, latch-free, and Spinlock-free. Okay, so you need those public symbol files, and you need to put them in the same directory under your under your SQL Server installation where your SQL Server exe lives. Okay, so big takeaway point, if you're using SQL Server 2012 onwards, you need more than that, just that one public symbol file. Okay, so how do you get these? There's a way of getting them using the toolkit that you get with a Windows debugger. The way I do it is I install Windows Toolkit. Okay, when I load up a trace, I just say trace load symbols. That will go away to the Microsoft public symbol server and download all the symbols. Word of caution, well, 2 words of caution. I won't do that now because I've done that already, because that is horrendously slow. Okay, so for people listening in on this, people who are watching this, if I was to download that, I may as well say to you, go away for 5 or 10 minutes, do some knitting, make yourself a coffee, nip down to the pub for a pint. It's going to take a long time. Okay, so I've downloaded them already, and this is the default location where it puts them. Okay, so the other thing you'll notice is these are actually these are folders that we can get into. So what you do is you actually copy those, you copy those folders and you put them in the same directory as your SQL Server executable. Okay. So let's start that event up. Yay. Okay. And we've got nothing running. So run this statement here, and that should return. We've got a row, but we've got no back off events. So what I'm going to do now is I'm going to introduce you to another tool called HammerDB. Let me. I apologise to anybody watching this, because this is small even for me. It's not a bad tool, but it's in terms of user experience and the GUI, it's not great at all. So let me. I wonder if I can change the resolution on my screen. Let me just minimise some stuff. Oops. Display settings, that might be useful. Display. So it's not something that I do that often. I'm sure it's under here. Okay, let me just fire this up. And what I'll do is, even though it's small, I'll talk you through it the best I can. Okay, so so what we do is you download this tool, and what you get is if we install it into a directory of your choosing. Let me just close that down, and we get this batch file. Okay, this HammerDB batch file. We'll fire that up. Okay. Options. Okay, so go with the eye strain this might cause. So we click on SQL Server in this pane in the top. So you want SQL Server, TPCC, which is an OLTP benchmark. TPCH is an OLAP one. We're going to go for TPCC. For anybody that uses any other different database engines, you use Oracle, DB2, MySQL, Postgres, Redis, and this thing called Trafodion, whatever that is. Okay, so I've never heard of that. You learn something new every day. Okay, so we get this TPCC branch up here. So the first thing we want to do is we want to build a schema. Okay, so you want to go for the updated version. So there's a schema, there's an original and updated radio button. Go for the updated one. Okay, and then we want to let's have a look at options. Yeah, we can specify a number of warehouses we want to create. So I'll just call I'll just say that's 33. Okay, so we're going to build a schema. Okay, we need to load the driver script. So this is very peculiar. So before we can move on to the driver script, we need to we need to stop the schema build. So there's one virtual user associated with that. Again, it's a nice little tool for simulating a TPCC workload. It's not the most fantastic tool in the world in terms of something that's just got not sort of nice look and feel for usability. Okay, so next thing we want to do is we want to load a driver script. So I'm going to accept all the defaults there. Okay, so we load that. That's loaded. Then we want to create some virtual users. So I've got i7 processor. It's got two cores hyper-threading, so I'm just going to go for 6, so not to swamp the machine. We'll show output. Okay, so I'm going to run that. Let's just see what's happening in Task Manager. And we can see that's ramping up quite nicely. So another thing we can do is we can fire up this transaction, this little transaction counter graph. You can see it's waiting. So let's just here we go. So we're doing the best part of we're just doing over 90,000 transactions per minute, and what will happen is we'll begin to see a there we go. We'll begin to see a nice little graph. Okay, so we've got a workload running. Let's run our let's run our SQL statement, see if we caught any back-off events. Oh, got 2 there. So let's see if we can accumulate a few more. Yeah. Okay. So let's have a look at this. Let's have a look at this XML. Okay. So this is the this is the Xdesk Manager Spinlock. So what does it do? This is a call stack. This will probably not mean that much to many people. So the question is, as a mere mortal, how can you make any sense of this? So there's people at Microsoft who can infer a whole world of meaning from call stacks. I've given people call stacks and traces before, and I've been absolutely blown away by the things they've told me about the database engine. They've said, this is interesting, Chris, and then they've gone headlong into a load of observations which, although I know a bit about the database engine, that I would never be able to make because I don't understand call stacks in the database engine as intimately as they do. Okay, so let's have a look at this. So XDES Manager. Okay, so our best bet is to actually, so this is a DLL. This is a C++ function it's calling. The best that we can do is actually look at the names of these things and try and infer some meaning from it. So we've got transaction here, so it's doing something with a transaction, so remove transaction. Let's have a look further down. Okay, so we've got remove transaction again. So get all this active XDES ID. Okay, so get XDES ID. So it's removing transactions and it's getting this XDES ID. What this XDES ID is, it's a structure associated with the transaction ID. So what this is with the sort of disk legacy database engine, there's a Spinlock that protects the part of the engine which gives out transaction IDs, because obviously it would be absolutely disastrous in terms of maintaining transactional consistency if you had sessions which obtain the same transaction ID. That would be game over. Therefore, we need to have something which prevents that. We need a synchronization mechanism, and for using the legacy engine, this happens to be a Spinlock. Okay, and what I'll do is I'll give you an overview of what these things mean, because as before, having a tool is perhaps not even half the battle. The real battle is actually inferring sort of information and knowledge from what the tool is actually showing you. Okay. So let's just stop HammerDB. Okay. So that was my little demo on simulating a simple TPCC workload and using extended events to dig into a Spinlock type. Okay. So perhaps the one big takeaway from this is it's not so much the tool itself, but it's just looking at the names of the functions and trying to infer some meaning from them. So back to the deck. Okay. So oops, no. We go back to where I was. So I've mentioned I've dived into public symbols debug systems. What are they? They are they're effectively text labels which associate language function method calls with a machine code instruction. Another point I should make as well is these are specific all the way down to CU level. So if you've managed to, if you're capturing call stacks using WinDBG, or you're using Windows Performance Toolkit and you've got the public symbols for a particular version of SQL Server, and then you apply a CU, what you'll have to do is you'll have to download the public symbols again, and they may or may not be there. Okay, so to the best of my knowledge, there's no guarantees from Microsoft. There's no hard and fast rules as to when they put them there. They are either there or they are not. Okay, so what is a call stack? Very good place to look for information, nice, clear, concise explanations, Wikipedia. Call stack is a data structure that stores information about the active subroutines of a computer program. So it's effectively, it's almost like a paper trail or the footprints of the sand of the subroutines that an active program has executed. Okay. So what do the DLLs in the call stack represent? From SQL Server 2012 onwards, Bob Ward gave a session, Bob Ward, wrong Bob. Bob Ward gave a session on this on PASS on SQLS and SQL Server 2012. What the database engine team did was they repackaged the way that the database engine was laid down in DLLs. So prior to SQL Server 2012, everything was wrapped up in one great big monolithic exe. In 2012 onwards, the engine team repackaged the engine into a number of DLLs. Okay, so this thing called SQLang.dll. So this is a T-SQL interpreter. It's responsible for statistics collection, result set rendering, query optimization. I believe that it also processes the tabular data stream as well. So query execution, iterators, memory grants, latches, spinlocks, also the column store batch engine. This comes out this thing called SQLmin.dll. The memory OLTP engine, you have a single DLL for the engine itself. You'll also have a separate DLL for every natively compiled procedural function and a separate DLL for each memory optimized table, and these are linked in with the engine dynamically. Okay. Expression service, you've got something that performs expression evaluation, basic compression, data type handling and conversion, SQL TST.dll. The query data store, okay, that's got its own DLL, unsurprisingly called QDS.dll. Storage engine, again, that comes out of SQLmin.dll. And then finally, SQL OS. Curiously, there's two DLLs associated with that. The SQLDK.dll, which is a SQL development kit, and SQLOS.dll. And bizarrely, most of the functionality for that is actually furnished out of SQLDK.dll. Okay, so I'm going to introduce you to another tool. This is this is more of a diagnostic tool than a monitoring tool. This is my favourite. This is Windows Performance Toolkit. This comes as this says Windows SDK. It actually now comes as part of the Windows ADK. I think it's Assessment and Development Planning Toolkit or something like that. Okay, so one important thing to do is to turn off this thing called the disable page executive. So what this uses hooks. This captures events using hooks built directly into the operating system. Okay. So there's various ways to run this. My preference is to use the xperf command line. So a nice little simple mind map here for how this works. So you need to start up a DOS command shell, and it needs to be run using administrative privileges, otherwise you'll get an error when you fire xperf on. So we start it up, we run a query or workload, and then we stop it to generate a file, and then we load the file into this thing called Windows Performance Analyzer. Okay. So I'll give you another demo. So I'm going to dig into Spinlocks with Windows Performance Toolkit. I'm going to investigate high CPU utilization with Windows Performance Toolkit. This really is a level 400 diagnostic tool. It is a bit exotic, but the Microsoft escalation team use this when they get cases of CPU saturation. Okay, so let's just close this down for a bit. Okay, let's go into Windows Performance Analyzer. So what I've got here is I've got a Spinlock, and what you can do is so what you do is you say File, you open your trace file, you say Trace, you load your symbols. Again, let's say already cached on your machine, that might take a while. And then what you do is you get this, you get these graphs over here. And what you do is you drag them onto this thing called the analysis canvas. Okay. So I'm just going to get rid of the stack on this one. I'm going to add in module and function. Let's expand this a bit. Let's expand our SQL Server exe. And then what you can do is the really nice thing about the changes that the engine team made in 2012 is that you can quantify the time across the different layers of the engine. So let's expand this thing here, SQL min.dll, and then we can see the functions in descending order. So let's just pick out a few things of interest here. So this is for the releasing of a latch. This is for the acquiring of a latch. Let's have a look. I did see a buff latch in here as well. So it looks like we're touching a page in the buffer pool there. Generating a log record here. So this, I like this tool a lot because not only does it give you the call stack, but it also gives you the CPU time across the database engine. It's this column here. This column is sampled CPU time in milliseconds across all logical processors. And the reason I like this is because it gives you a 360-degree view of the database engine, not just the view that Microsoft think you should have via DMVs, via extended events. It gives you the whole lot. You can get the public symbols. It will give you a view in terms of where your CPU times get going. Okay, so what we can do is we can add in the stack. Okay, so let's expand this, and then what you can do is let's see if we can find a Spinlock in here. Okay, so something else we can see that apart from these two DLLs here, the SQL Server is nearly bare metal onto the hardware. So let's just walk the stack and see if we can find a Spinlock. So I'm not finding one as hyper as a stack as I'd like. So what you can do is, if you see a Spinlock, so imagine this said Spinlock in here, you can right click on this and you can say view callers by function, and what that will do is, if you look in this analysis window here, I've already done that, it will show me all the functions that have called this Spinlock. And the value of this is that not every, so latches are, there's a section on the SQL Skills website which does a fantastic job of documenting latches. I don't know of anywhere where the Spinlocks are documented. So this is a really good way of filling in the holes when you've got missing documentation. Okay, so back to the deck. Okay, so I've covered the legacy engine. I'm going to just touch briefly on the in-memory engine. I'm guessing there's people that have heard of Postgres, may have heard of Ingress. There's a guy, I mentioned him before in some article, a guy called Dr. Michael Stonebrake. He works at MIT, and I think he won some sort of Turing Award for computer science, and he's done lots of design work with database engines, written lots of papers, and what he said the problem with a traditional database engine is that only 4% of its time, wall clock time, is actually spent doing useful work. The rest of the time it spends on things such as latching, locking, recovery, and buffer pool management. Okay, so what to do? So the SQL Server in-memory engine comes to the rescue here because it's 100% lock and Spinlock free. It's 100% latch free. Code can be natively compiled. One of the big problems with the legacy engine is it is tremendously heavy on the logging infrastructure. So use the in-memory engine, and it doesn't log any undo. It doesn't perform write-ahead logging. It's very the records it does log are for logical operations. They're quite large, but it's very, very aggressive at aggregating them together. Okay, so question: we've got this beast. It's lock free. It's spin lock free. It's latch free. So where's the art in using this thing? Okay, so I'll just touch on some architectural aspects of this. Hackathon.dll is the sort of container for the in-memory engine inside the legacy engine. Okay, but Hackathon.dll it's a self-contained entity, but it still uses things from the legacy engine. So it uses this thing called a metadata cache Spinlock, which I'll get onto. It uses all the legacy stuff for backup and restore. It uses checkpoint files, but it still uses elements of the backup and restore functionality. Okay, it uses logging infrastructure for logging and logical operations. It uses the legacy engine for the management of joint transactions. So there's two ways to use a memory optimized engine. You can use them in a legacy engine or natively compiled store procedures. If you use them in the legacy engine, you have this concept, this thing called a joint transaction. It spans both engines, and there has to be a way of coordinating that activity. Okay, and then finally the allocation of large pages. So first point is that with the in-memory engine, there's two types of indexes, a thing called a range index and a thing called a hash index. A hash index is used for point lookups. You try and use it for a range scan, and the entire index will be scanned from beginning to end. For certain use cases where this is better, so it's better for singleton inserts and also point lookups. Okay, whereas as the name suggests, the range scan is much better for range scans. Surprise, surprise. Okay, so this graph here illustrates that we get much better scalability with the hash index than the range index for singleton inserts. Okay, so the second point is bucket sizes. Okay, so what Microsoft recommend is that you have at least one bucket per distinct key value. Okay, so I'm going to dive into a bit of computer science oriented maths here. This thing called big O notation. Okay, so that's this thing here, this O with one followed in brackets, and what that means is that's a computer science way of expressing the time or space complexity of an algorithm in relation to the input data set size. Okay, so if we avoid collisions on our hash buckets, i.e. we don't have this long, we only have one item, we avoid having to scan through the hash chain because we're getting collisions. The algorithm behaves in a order one fashion. That means that we hit the bucket, and irrespective of the size of the input data set, the scan time is constant. Okay, so if we start getting collisions, the sort of time complexity of the algorithm changes, and it changes this thing called order n, and that means that the time becomes linear depending on the number of items in the input data set. Okay, so another point: avoid joint transactions. The in-memory engine, it's lock-free, latch-free, and spin-lock-free. However, if you instigate transactions in a deep legacy engine, you'll get there's this thing called the blocker enum Spinlock, which is used to. So if you look here, SQL min.dll full exat int base allow transactions. That coordinates the transaction mobility between both engines. Okay. Another big point as well is that we use this thing called XDES manager. Okay. So you want to avoid using these Spinlocks. So what you want to do is you want to use natively compiled store procedures wherever possible. Okay. So as mentioned, use natively compiled procedures wherever possible. If you do not, you will get Spinlock activity. Okay, and then also using a conventional store procedure will also include overheads interpreted T-SQL language in SQLlang.dll. I've got SQL, my apologies, I've got SQL min, that should be SQL lang, but it's definitely SQL lang. So that is why you should avoid joint transactions. Okay. Another final point as well is there's prior to SQL Server 2016 CU2, there's this nasty bug whereby you can burn up a lot of CPU time on this thing called the metadata cache protection spinlock, which manifests this thing called CMED hash set, which on face value is pretty meaningless, but I can assure you that what that does is that does protect this thing called the metadata cache. And what the engine team have done with CU2 is they've replaced that with a read-write spinlock. So what that means is that for read access you don't spin. Okay, so on this particular test, just on my main test machine with 2 sockets and 10 cores per socket, I managed to create a scenario whereby I expended 40% of the total CPU time on the box on that one spinlock. Okay, and finally, before I wrap up and take questions, the last community event I was at was at SQL Saturday Holland, and I spoke to a Dutch guy that works for Microsoft, and he mentioned this thing, this piece of work that Microsoft had done. They'd used the in-memory engine, they'd used column stores on memory optimized tables. This is SQL Server 2016, and they'd used the R capabilities of the database engine, and they'd used it to come up with some benchmark which was based on how many predictions per second they could perform. And the reason I mention this is because, you know, there might be people thinking, oh, OLTP, it's old hat, it's, you know, it's been done to death, it's not exciting. This for me puts a very new, interesting and unique spin on it all. Okay, questions?
Okay, Chris, thank you very much for that. That was great. All right, first question. You can hear me, can't you, Chris?
Yeah, I can hear you.
I wasn't sure. Okay.
So I can hear your dulcet tones.
Yeah, good. I know you like them so much. Anyhow, let's kick off. So, first question. You talked earlier about the performance monitoring and taking metrics and maybe recording stuff from the DMVs and perf counters. One of the problems with that is the sheer amount of size and space that is required to store all the historic stats. Now, do you have any recommendations on how to deal with that problem?
Well, I've got my I've got my own tools. I mean, the obvious one is to keep the sort of base counters that you're collecting down to a minimum. So that, you know, there's obvious ones you want to collect: batch requests per second, compiles, recompiles, stuff around locking, PLA, PLE. Keep the calls set down to a minimum, and then once you get a problem, you think there's something you need to dig into. Yeah, just add them. So an example which is always useful, I did some work with somebody that used Dynamics CX, and that's exactly what we did. We set a trace collector going. You know, we started off with a core bunch of counters. We kept going over a few days, and that was quite manageable. Something else that I've got my own tools which just capture core stuff for them. So the very core basic stuff I'd capture would be the top non-idle wait events, latches and spinlocks. I mean, I'm guessing, you know, people out there have got their own tools. I'd be absolutely shocked, horrified and mortified if there wasn't something incredibly powerful and cool on the DBA tools website. But the short answer is, you know, keep the core things that you're counting to a minimum. I mean, the really important thing is that anything that's performance related, people, and I'm guilty of this, have got a tendency to dive headlong into the internals. But the one, the one most important metric of all is the thing that's important to your business. So, if you've got Mark Broadbent Global Industries, and this thing is manufacturing widgets, and the more widgets it can manufacture a second, that means the more money flows into Mark Broadbent's bank account. Obviously, that is that's the key performance metric that you want to look at.
Absolutely. Cool. You talked about Spinlocks earlier, and Spinlocks using backoff. Does SQL Server actually prioritize Spinlocks at all, or are they all treated exactly the same?
It's right. Okay, so Spinlocks. Take a step back. Spinlocks are not just they're not strictly a SQL Server entity. They're not even strictly a Windows entity, because you get Spinlocks in Linux, you get Spinlocks in the Windows operating system. One of the things that the engine team did with SQL Server 2008, they rewrote a lot of Spinlocks. So that what the database engine did was it had its own native Spinlock. So I'll give you a nice analogy here. So if you want to open a door to a particular room, say if you want to, let's keep this polite, let's just say you want to get into the bathroom and somebody's locked the door. Okay, what you might do is you might go up to the door every so often and try and turn the doorknob, and if it's locked, you'll back off and you'll try it again. The more intelligent way of doing that is to actually look at the doorknob on the outside of the door and then wait to see if that turns. So that means somebody's coming out and you can jump in. The problem with that is that there's like a window in time which somebody else can jump in even though you might have been waiting longest. So what I've been reliably informed is that in SQL Server 2008, to avoid this scenario, what the database engine team did is they brought in these things called queue Spinlocks, whereby it's got some concept of ordering in order to prevent people from jumping in before you.
Cool. Okay, sticking with Spinlocks. So this question says, if we are observing a high proportion of Spinlocks, can we always assume that we have physical resource problems such as not enough memory, slow disk, or not enough cores?
Okay, unfortunately there isn't a simple answer to this. There's some Spinlocks that you can turn off. Okay, so there's a Spinlock called opt_IDX stats. That's associated with internal data structures use the missing index feature. You can turn that off with trace flag 2330, I think it is. So that's an example of a Spinlock that you can turn off completely. Okay. There's some Spinlocks which you don't have a lever or knob to control, so there's a lock cache Spinlock. So if you've got a hot bucket in the lock manager table, you might have, if you've got lock escalation, that might cause the bucket to be hot. If you've got locking on a particular row, if your indexing strategy is not quite right, if you've got a bad plan, which means you've got lots of SQL statements hitting a particular row, but they're taking longer than normal because something's happened to cause a plan from flipping from using an index seek to a full index scan. That is an example of things that you can do to sort of lessen the impact on that Spinlock. Okay, so that is so the first type is there's some that you can turn off with trace flags. Second type, as I mentioned, is some that you can lessen the impact on based on the way that your application is designed and coded. Now the final type, and this is the real great white shark, is there's some Spinlocks that you have to take a hit on. They're like the final wild performance frontier. So I mentioned log cache access. There's only two things that you can do with that. You can give the log writer its own CPU core. Above and beyond that, the only thing you can do is what I call the brute force technique to solving that. And what that is to do is to use a CPU with the fastest single threaded performance possible. Also, if you can consolidate your workload on fewer cores and fewer sockets, that will help as well. If you've got spin locking issues, adding cores will more likely actually exacerbate the issue rather than resolve it. So the question is, what can you do? Is it shortage of resource? The answer is it's a combination of how your application is behaving, how it's designed. There's some spin locks you can turn off. There's some that you can lessen the impact on by the way that your application behaves, and then there's some that you just have to take a hit with. And if push comes to shove, the only place to go is, as I mentioned, is the brute force approach. So this latter category of spin locks is mainly around the logging infrastructure. The only other place you could go is to consider the in-memory engine, because as I mentioned, if you use natively compiled stored procedures, it uses a lock-free transaction map instead of XDES manager, and it is an order of magnitude lighter on the logging infrastructure because it logs less, and also because there's no undo generation, there's no write-ahead logging, and also it's really ultra aggressive at aggregating log records. So I apologise if that was a bit of a wordy answer, but that is essentially it.
Wordy was an understatement.
Yeah.
Right, so since you mentioned the in-memory OLTP, the question here is, I think you alluded to the fact that if you're running interpreted TSQL that you would potentially get Spinlocks, but the question says that would you still get Spinlocks by using interpreted TSQL if you're only accessing in-memory tables?
You get Spinlock activity. The level of Spinlock activity you would get is entirely dependent on the load. Another point I should make is, based on the work I've done, is that I've gone out my way to basically, you know, put the database engine under pressure and make it feel pain. Based on the work I've done, you need 2 sockets, you need at least 6 calls per socket. So there's a lot of people out there, if they've only got 2 sockets and 6 calls per socket, they're never ever likely to see a Spinlock issue. So the answer is it depends on the nature of your application and how many CPU cores you're throwing at it.
But presumably any accesses to that in-memory data won't have the normal Spinlock overhead that you would normally get. So what I'm trying to say is you'd have a better scenario than if you're just using on-disk tables.
Oh yes, but the key thing about that is if you can, always use natively compiled stored procedures, because what that means is it means you're using the transaction manager inside the in-memory engine, which is Spinlock free.
Right. Okay.
Yeah.
Cool. All right. So you talked earlier about the hot page problem. Now, traditional advice, if this is accurate, has always been to avoid GUIDs in cluster keys. But you say it's best for scalability purposes to use them, but when should you not use them, and also should we now always avoid sequential cluster keys?
So the question is, it's forgive me for mentioning this. This is a it depends question. If you've got an application And if for whatever reason you have to use legacy engines, therefore you're going to run into latching. And if concurrent insert throughput matters to you, you're going to have to come up with a strategy of using some random key. So I mentioned there's 3 strategies. Okay, so you can use you can randomize a key. GUID is one approach. You can use hash partitioning, or if the number of rows you're talking about is not that great, you can pad the rows out. If you're if highly concurrent DML throughput doesn't matter, you can probably get away with a sequential key. So it all depends on it all depends on your workload. The workload is the thing which dictates the strategy.
Right, so going to SQL 2016, you mentioned that it had multiple log writer threads. Can you can you clarify again how many threads you actually get, and does that change?
To the best of my knowledge, you get 4 threads, and they always appear on numer 0.
Oh.
I mean, the interesting thing is that I'm yet to actually fathom the problem that this change the engine was introduced to solve, because I've used it with conventional durability, and and with low latency storage, it's as fast as using a single-threaded log writer. There's no difference in performance for OLTP throughput. If you've got low latency storage and use delayed durability, it's actually worse, because you start seeing lots of spins on a log flush queue Spinlock. That creates, because the log flush queue begins to back up because the log writers are fighting on a Spinlock, that creates back pressure on the Spinlock protecting the log buffer.
Right. So from what you say, can I infer from that we should maybe consider setting an affinity for SQL away from numer 0, or is that something you shouldn't do?
It's not something you should do ordinarily. So if you're seeing spins on a log cache access Spinlock of the order of billions, you should perhaps consider taking core 0 out of the affinity mask for numer 0. But you're going to have to be pushing the engine quite hard. So if you're working for a gaming organisation, so if you're working at Mark Broadbent Gaming Incorporated, or
I wish I had all these.
Well, you do, Mark. It's just that you don't tell anybody. But if you're working at a gaming company, because I'll be frank, a lot of the material I write, I may as well just rename it, just say SQL Server for gaming companies, because they seem to be the sweet spot. Or you're some sort of trading organisation, or if you're I don't know, you've got some software as a service. So Domino's Pizza, for example, during the Super Bowl, they were like one of the most, in terms of transactional throughputs, they have one of the most active websites in the world. If you're of that ilk and you're using SQL Server and you're using legacy engine, you'll be really killing that Spinlock, and there's probably there is value to be had in taking core 0 out of the mask. For most, but there'll be a lot of SQL shops that just don't see that pressure, because they haven't, they've got no requirement to have, loads and loads of CPU cores, and they just don't have a massive OLTP workload.
Okay.
So okay.
Sorry to cut you there. Right. So, are there? I guess this question isn't really an are they, it's what are the performance implications with in-memory OLTP containers being on slow disk?
Well, okay, so this is the I presume you actually mean the containers which you use for the checkpoint files,
Yeah,
yes?
I think it's relating to the checkpoint threads.
So, I'll be brutally honest here, and this is something that I intend to look at, but it's not something I've looked at. But so there's a bit of a notion that because it's in memory, you don't need fast storage. But the sort of counter argument to that is you probably want to use the in-memory engine because you've got business critical performance. Therefore, if for any reason your instance goes down or it fails over, you want to be able to reconstruct your the contents of your memory optimized tables if you've got durability as fast as possible. Therefore, you most definitely do need fast storage, and I suspect that there's I'm sure I've read something somewhere that there's a direct relationship between the number of containers and the actual ability to reconstruct your in-memory data. So what I'm saying is, I think the more containers you have, the more beneficial that is for the actual throughput when reconstructing your in-memory data.
Yeah, I think I've read the same one as you, and I think the article. So you get, if I remember this correctly, you get a checkpoint thread per container, and I think the article you and me have both read discusses how many containers you should actually aim for, because I think if you have a scenario where you have two containers on two disks, then because you have the data and the delta, which will eventually flip-flop on essentially the same disk every single time. So I think the article that you and me have both read actually talks about trying to avoid having the same disk hit for the same operation. But yeah, so if anyone's listening out there, I would advise to do a Google for that article, which will probably be on in-memory checkpointing. Right. Okay, so you mentioned trace flag 3656, and I think it was fairly clear that you had installed the public symbols on the server in question. I think you need them, don't you, for that trace flag to actually work? And so the actual question is it advisable to have those public symbols installed in reserve on a production server on the event that you actually hit a performance problem?
So there's two scenarios. So if you're using Windows Performance Toolkit, you can gather a trace anywhere. You can run it on. You can analyze it on any other machine that's got Windows Performance Toolkit on, which has got symbols. If you want to use that extended event trace issue in situ against the production system, you need a trace flags there. And again, it's probably not a bad idea to have them at hand because, as I mentioned, the first time you download them, they go into a cache, but the actual the download can take ages. Another thing I've noticed is that there are times when the public symbol server can go on a go slow.
Right.
So I don't know whether there's some sort of maintenance or housekeeping that Microsoft perform, but there are times when it's not particularly fast, but there's times when it is painfully slow. So the short answer is yes, there's probably value in downloading them ahead of time.
Cool. I mean, if they're not being used, there is no overhead other than storage for them being on the server. It's okay.
No overhead whatsoever.
Excellent.